Hello, everyone. Good morning and good afternoon. I would like to introduce Pawel Malinowski. He is the program manager at IMEC. Today, he's going to be talking to us about Imec's high pixel density infrared sensors enabling augmented vision. Um, with that, I'd like to give it over to you, Pavel. And we'll,
Thanks, Greg.
um,
Thanks and welcome everybody wherever you're connecting from. It will be great to see each other live. So here I can only hope that you are somewhere out there. Thanks for connecting. Thank you, TechBlick, for organizing the platform and the event. Really nicely done to substitute the live events. At least we can have the sense of community here. And I'm happy to talk on behalf our TFPD team at Imec, and I will show you what we are doing with quantum dots for image sensors. Imec is located, the headquarters is located in Leuven, just east of Brussels in Belgium, where I'm also connecting from. We are independent R&D organization. We are mostly known for our work on semiconductor scaling and pushing the limits of photolithography. We've been operating since 1984, and in the meantime, we are around 4,500 people with almost 100 nationalities. And one of the characteristic things is that most of our budget comes from industry and industrial partnerships, and we are proud to work with more than 600 companies. So what we do is typically we do research for companies and with companies. And next to all the semiconductor scaling, we are active in image sensors. And one of the trends that we see in image sensor development is that it evolves from designing sensors for photography or to best replicate what the human eye can see. You have lots of applications in different types of machine vision where the output doesn't need to be really an image, but you want to get data that is specific for a certain application. The consequence of that is that you have quite a fragmented field because automotive sensors will have completely different specs than microscopy sensors, for example. But it gives a lot of possibilities for customization and for optimizing the sensor for particular application. One of the things that is very interesting is to go for what we call augmented vision, or have the image sensors that detect wavelengths that are not discernible for the human eye. And a lot of these machine vision applications, they need this additional information, for example, from the near infrared or shortwave infrared range. If you look at the spectrum that comes to Earth from the sun, you see a lot of characteristic peaks and valleys. If you are in the valley, this is a good region to work with active illumination because you have very low background. Switching from a typical 940 nanometers to around 1400 gives you even less background radiation, so you can have better contrast. If you want to work with passive illumination, so with the light that is already there, around 1500 nanometers, you have a good range where you have a lot of this latent light that can be used, for example, in low visibility applications, like for surveillance and security. Now the problem is, how do you make sensors for these wavelengths beyond what silicon sensors can see? Also to operate in the eye-safe region, which is above 1400 nanometers, where the human eye is around 1,000,000 times less sensitive than in the visible. What we define as TFPD, or thin-film photodetector technology, we place it between the very standard CIS or CMOS image sensors and the 3.5s. The CIS is what we all have in our pockets in the smartphones with high maturity, super high throughputs. Now we are at around 6 billion units per year. Low cost because of the scale, very small pixels, big flexibility of design, but because of the silicon limitations, no sensitivity in the shortwave IR. For that range, typically use 3.5 or 2.6 materials as the absorber. That has to be integrated on top of the readout, typically by means of flip chip hybridization.